is the corrosion in a particular region on the structure? So sometimes you get, in the facade, you get corrosion a couple of millimeters or even centimeters away from the edges. Okay. The bird's eye view is to see where is the source. Is it carbon dioxide coming from, like in wind direction? Or is it a fog coming from one direction? Then the next question is, why is it few millimeters inside and not this side, as well as the front, which is taking all of it? Okay. So determining all of that will help you to know the source of it. So if you're closer to the sea, and you're highly likely it's the tallest building in the neighborhood, everything else is small, then you can expect there will be a wind-driven salt coming in. And that means it probably won't affect the lower part of it, it'll probably affect the top part of the structure. And it will be heavy loaded on the front, so you will expect corrosion in the front. But if it's wind driven, wind has a particular nature of coming around the building, so it'll affect on the front anyway, but when it comes around, it probably creates an eddy current at the back, so it might actually go and attack the sides of it, just inside the structure. So all of this interpretation depends on how much high you can look at it. The unmanned aerial vehicle technology is so far advanced, you can just send a drone or a UAV. We don't call it drone, it's because drone is now military technology, and the UAV is the operator technology. I don't even know if it's allowed to be operated in India. In the US it is. You can go up to a certain height. It's allowed. Okay. Up to a certain height it's highly likely to be allowed. Above that you need civil aviation. Up to 120. Okay. That means it's very similar to US. They have something similar. Okay. You need the landowner's permission as well, I think. So you can do that in your house up to 120 meters. So that means you get a view of the structure, and then you can decide, is it going to be coming in from? Now, going further on the structure, can you tell whether it's fluorides or carbonation? Not easy. It's not easy to say that. And it depends on the cover depth, essentially. It depends on if the corrosion is uniform and you're in an environment where carbon dioxide is high, you can expect that. But if you're nowhere near the sea, you have no other source of salt, unless within, you can then filter it down as carbonation. You'll find out in a few minutes anyway. If you drill it and spray, you will know. Okay. But other than accessing the structure, it's hard to tell. I find it hard to tell. Maybe others have a different technique of it.
Not to give a opinion, public investigation.
Yeah.
No. As I am the public,
yeah.
If my building is maybe a problem, how can I call the engineers to for repair? Suppose before going to that, it may be subject to corrosion.
Yep.
Then only I call the concern expert.
Yep.
So I have the knowledge with respect to this physical inspection.
Yep.
I can come to particular thing. That's why.
Okay.
But in general, here red batches will come. So may be subject to corrosion. For this study, we are going in depth with the carbonation as well as the fluoridation corrosion.
Yep.
If you have any color difference or any distress identification, it's going to be used for hotel. That's all.
Sorry. Oh, are you adding to it, or were you asking a question yourself?
How will distinguish?
Okay.
Is due to physical.
Not by. Sorry.
Only by visual appearance.
Physical appearance.
I don't think it's easy, because looking at a structure that's corroding, it's not going to be easy. Carbonation generally will have a general corrosion, so you will be able to see the trace of the rebar. You might have a leaching from it of ferrous hydroxide. You will get ferrous hydroxide leaching for chlorides as well. But we're talking about pitting corrosion. But that may not happen if you have chlorides inbuilt. You will still see the rebar line, you will still see the leaching. So it's not going to be an easy task. You will need to go access the structure. Now, one of the tricky thing about getting down to an answer is to keep an open mind, because quite often the answer is what you're not expecting. We can go to the structure and we can expect that these are likely to be the problem. There's salt here, there's CO2 here, that's fine. You might find that they already had used salt in the mixing. Or you might find there's like aggregates being reactive, or you might find there's moisture movement within the structure, or thermal movement. It can be any number of reasons. So it's important to keep an open mind and important to keep a checklist in your head. I can have any number of problems. So if you have a bigger view, then the number of problems will be that you can tick off will be higher. But that means you can do your inspection and investigation to filter it down to a small number of issues. Ultimately, you should take a decision after seeing the concrete. You should not confirm everything without testing the concrete. Because let's say you've looked at it and on the front it is carbonation, okay? And you're reporting that it's carbonation, it needs to be fixed. What if it has reactive aggregates that we haven't seen? But in the timeline of that structure, you as an individual has given a report saying it's carbonation. Your report is available and accessible. But it might have reactive aggregates that we didn't look at. I don't know how the liability worked, but in our walls, in the UK, as an engineer that I've signed off, I'm liable. I should have seen it. I should have looked at it. And I would assume that you should take such an approach. Take a sample always. Petrography is not an expensive technique. Send it to petrography. Be sure that I'm not worrying about anything else. I shouldn't be worrying about anything else. So there's minimum things that you should do. Petrography, in my view, is one of those things. If it is not cheaper, it will become really cheap because they do these samples day in, day out. They're so used to the mineral makeup, they can tell by looking. It's this and this and this. And when we look at alkali silica reaction, we'll see when it's reacted, it is fantastic. It looks beautiful. Does that answer the question? You can't be exact very quickly. You shouldn't be. Make them pay for your time anyways. Because ultimately if you go really fast, you can miss things. And that's not something we should have in our books. In the grand scheme of things, the cost that they pay for your time and the testing is smaller compared to the lives. That may depend on the structure afterwards. So, alkali silica reaction is just like any other internal reaction. It's a reaction from within. The structure cannot. Sorry, before I progress, does anybody else have an opinion on that? We were talking about, can you visually inspect a structure and conclude the decisions?
It is practically not possible and it's not even accepted.
Okay. Yeah, I would agree with that. However, it's not so far in the future we will be able to do it, but not with human eye. Okay, so you guys are using UAV. We're looking at unmanned aerial vehicle for material identification. So that means we lift an unmanned aerial vehicle with different camera systems, infrared as well as sometimes laser scanning systems, to look at the material. So unmanned aerial vehicle can be used to draw the building very fast. It's game technology for those who are into games. So we can lift something up, we can rotate it, and we can build a picture of that, scaled picture of it, very quickly, and then put on top of it the actual image. So you can make a 3D image of your structure really fast, and you're also capturing all the surface, everything clearly. And added to that, we're looking at, it's not ready yet, but we're looking at the laser to see if we can capture the particles, to see what is it that we're looking at. It's very complex because it's bigger, bulkier, costly, too risky because it's high up in the sky. It might become very cheaper later on. I don't know. We can expect that because that seems to be the driving force in the technology. Much easier to have the bird's eye view with the UAV now, which means you just lift something up and you can get a full picture. Fantastic. Okay, can I move to ASR? So ASR will give a definite cracking pattern on the surface. People say map or star cracking. I've looked at structures that might have those issues. It's quite hard to tell it's map or star cracking, but I can be certain that there is an internal reaction. That much certainty is sufficient because I am then focusing my investigation that way. So ASR is the alkalis in the cement reacting with the reactive part of the aggregates. Okay. So that means you should see a colorful compound around the aggregates. May not be visible visually unless it's gone that far, but you can see that through an optical microscope. Optical microscope is not really expensive. Again, petrography will send you a very nice fluorescent picture. They take a section of concrete where you tell them to take. So this is a core, they cut it and they take a section and then they grind it down further so that you can almost see through the concrete. Called a thin section. They put the thin section under a microscope and they can move around and they can see different parts of the structure. And one such image will look like this. This is a reacted aggregate. I think you use more pictures. On the surface you see cracking. Okay? Internal crackings all have a kind of a pattern. It's very similar to geological pattern. So if you look at a geological rock formation, it'll have a definite structure. And that structure is to do with the mineral makeup. The mineral has a shape, and that shape will come up to the top in a larger fashion. Similar to that, your internal forces, whether that's due to expansion or any other sulfate-related attack or alkali-silica reaction, you will get a cracking pattern. More in tune people will say that's a map cracking. Maybe they're referring to the contours being complete. I'm not yet sure. This is what you should see. You should see a reaction rim around the aggregates. Okay? Huh? Reaction rim is the gel. So most of the aggregates that we use are crystalline, strong aggregates. Okay? The reaction rim is something that has changed its shape from crystalline to a gel, to an amorphous substance. That reaction is due to the alkali affecting the silicate part of the aggregate and getting them into a gel. So it has no structural integrity. It's a gel. And that gel condensifies on the outside because that's where the alkalis are. And that's where it forms. Which means remember the picture yesterday where I interlocked the aggregates and refined it? There's no interlocking anymore. The aggregates are independent, which means it has no structural integrity. If you put a loading on it, it'll just fall apart. Okay? That's the power of internal reactions. Does the property match with the CSH gel? Not sure. Does it? Not necessarily. If you have sodium is one of the alkalis, so it may not be calcium silicate, it may be sodium silicate. So it's not the calcium part of the alkali, I think. In the cement, we will look for how much sodium oxide is there and potassium oxide. I can look up and see what the gel formation is. We have samples in the lab, historical samples. It's a matter of sending them to SEM and we can tell what's in it. So, any questions on this? The first part of that word ASR is aggregate. Alkali silica reaction or alkali aggregate reaction, second part, which means it'll be around the aggregate. Okay. So if it is around the aggregate, you can expect the aggregate itself is reacting. Okay. If it is around something else, then you should be looking at that part. So the halo that we're talking about, or the reaction rim, will be around the aggregate, and that's very definite. See these white colored particles? The gel might move. That's the reaction room in a different, it's a fluorescent picture. Let me see if there's more fluorescent picture. There you go. So this is part of the fluorescent microscopy, so you can see the halos gently, but you can see that the aggregate is broken. Okay? So all these fine cracks means there's internal reaction. And that's how you start looking at, I have internal reaction, what else do I have? Happy enough? Okay. So remember the thin section that I mentioned? But before they make the thin section, they flood the area under high pressure with the fluorescent dye. And then they grind it. And then when you look at it in the microscope, you see this. People say some of the cracking can arise due to the grinding process, so you just need to be careful in diluting an answer. Can you do SEM on this? I don't think so, because you've put the fluorescent in it. But you can use thin section and transfer that to SEM. Yes, you can. Or you can do the other way. You can do the SEM and then you can grind it further. Maybe the other way is better. SEM, depending on the SEM, we have two SEMs. One is called an environmental SEM, which doesn't need you to put a coating. The other SEM, which is the most expensive physics SEM, they put a gold nanoparticle coating. I don't know what color is gold nanoparticle coating. It's definitely not yellow anyway. That means you've affected the surface, so you probably will need to grind it. Okay? So, if you look at, so the alkali silica reaction can happen due to larger aggregate and also can happen due to aggregates in the form of sand. So they're very reactive minerals. If you ask any geologist, they will explain the reactive minerals. So if you're in the concrete business, you need to have a geologist in your team, because they can look at it, even they can look at it and say, well, that's a reactive aggregate, don't use it. You're digging the earth to get that into concrete, so you need to have very quick decision makers. They have a very trained eye, and my eye doesn't train to the geologist's eye. So this is, I think it looks like a sand particle reacting, and you can see the halo around the sand particle. Okay, and that seems to be this seems to be the rust formation. I don't know what that is. It could be the dye. Okay, so ASR, how can you prevent ASR? If you want a picture, I can go back. Okay, how can you prevent ASR? Or AAR? So you always go to the root cause of it and you try to avoid it. Okay? So ASR, the first part is aggregate, isn't it? Without which the reaction won't happen. So avoid any naturally reactive aggregates. First thing. And that's good practice anyway. I think some of the codes might allow you to add up to certain percentage of reactive aggregates. Very small percentage that would be. If you can, don't take the chance. If you can't, then take a calculated chance. So avoiding the aggregates is the best strategy. And what else is the next strategy? Here's your sodium and potassium oxides reacting. So it's not the calcium part. Yeah, we've explained that, so I'm coming back to the things. So the reaction is due to reactive aggregates, yes, but the root cause of the reaction, other than the aggregate, is the alkalis. Okay, where does alkali come from? It's from the cement. Okay, so if you can use the cement-less concrete, that's great. It's not possible, not yet. But that means you need to use a cement with lower quantity of alkalis. Which cements does have lower quantity of alkalis? Cements with lower alkali. Alkali is quantified quite often as the pH, or the net pH of the cement system. So which cement systems have low pH? SEM1, is that how you classify here, SEM1 or PC, Portland cement?
Yeah, we can classify with name.
Okay, So, okay, so ordinary Portland cement, okay, that's very similar, yeah. So ordinary Portland cement, I'm assuming is very comparable to the European coding called CEM1, which means 95% of it should be Portlandite part of it, or the calcium silicate hydrate part of it, and aluminase, but it should be Portlandic more than any additives, but you're allowed 5% additives there. Okay, and that could be anything. It could be PFA, that could be fillers, it could be 5% can be anything. They're not required to explain what is it, but that means it has the highest